Hello. Let's do some calculus. It's kind of a review. Oh dear. Review document for 10.1, 10.6. Getting ready for a little quiz. So let's see. For what values does this series converge? Well, x would definitely have to be some kind of negative exponent, right? Because if we're going to have any chance at all, these things need to be getting smaller and smaller, going to 0. So have to be negative values. So that allows for things bigger than -1. That's no good. That's no good. Definitely not all values of x. So it's this or this. So let's see. If x was -1, that's actually the harmonic series, isn't it? And the harmonic series does not converge, but if that exponent was anything less than -1, -2, -3, or even -1.01 or whatever, then it is going to converge. So that's just a matter really of recognizing that this is a way of stating a p-series. It's just kind of the upside down of what we usually do. N to the p, right? All right, so that's the answer. Which of the following series converge? Let's see, this is a p-series with p greater than 2, so that converges. This is the harmonic series. That does not converge. And this is an alternating series, so for an alternating series to converge, the only thing that has to happen is the terms need to be getting smaller in absolute value going to 0. So this passes the test. If it wasn't alternating, then the p would be a half, and it would be no good. But it is alternating, so it is good. So that's 1 and 3. Which of the following series are convergent? Hey, I just answered that question, didn't I? Oh, and look, there's the harmonic series again. And there's that p-series again. This is like, it really is the same question. And here's an alternating series. And this actually would, this is a geometric series with a first term of 1, and a multiplier of -1/3. So that actually is that 4/3, so 3/4. So this, not only does this converge, we know what it converges to, which we cannot say all the time. And it also, so it's alternating, so like, you know, the geometric series doesn't need to alternate to converge if the r is between -1 and 1. But if it does, then all the better. How about this? In my experience, this question has caused some confusion for students. So we're going from I starting at n up to infinity. So when in doubt, write out the first few terms of your series. 1/3 to the n, and 1/3 to the n plus 1, and then 1/3 to the n plus 2. Hopefully you recognize that this is geometric with a multiplier of 1/3, right? So let's see. The sum of a geometric series is the first term over 1 minus the multiplier, which is 1/3. So that's 2/3 on the bottom of this. Dividing by 2/3, same as multiplying by 3/2. So that is it right there. Got to think, you know, if somebody's actually asking you what is the sum of a series, kind of has to be geometric, right? I mean, it's the only kind that we really know how to find the sum for, at least at this point. Which of the following series converge? This is alternating, so the only thing that needs to happen is these terms need to be going to 0, and yep, they are. Let's see. How about this? Well, these terms, this is like a geometric series, but the multiplier is 3/2. They're getting bigger and bigger, and this is the harmonic series. So by limit comparison we could do, if you wanted to make a justification for that. We don't have to because this is just multiple choice, but this is a series that doesn't converge times something that's bigger than 1. So that ain't not convergent. No chance. This is a tricky one. What do you do with this? Well, every once in a while you actually have to do the integral test. So let's see, if we make the function version of this, then you're like, well, what am I supposed to do with that? Well, what if you made u equal to natural log x, then du would be 1 over x dx, and there it is, 1 over x dx. Now, lo and behold, the bottom here, that would be natural log 2, it's still going to infinity, and this would be 1 over u du, and the antiderivative of that is natural log u. So this does still blow up, because that goes off to infinity. Very slowly, it's a sad story, but that diverges, so 1 only. All right, how about these extra practice problems? For a equals 1 to infinity, let a sub n be this. Write out the terms from n equals 1 to 4. Oops. Get a blank piece of paper here. Now this is a sub n is equal to 2n over n plus 1. I want to write out the first 4 terms, but there's an alternator stuck to that, so the first one is going to be negative. And this is in sequence notation, so I'm not adding them up. It's a list of numbers, so I should have commas in between them. When I plug in 1 into 2 times 1, that's 1. When I plug in 2, 2 times 2 is 4 over 3. When I plug in 3, I get 6 over 4. And it's alternating. When I plug in 4, I get 8 over 5. That's the first 4 terms. I think I did okay there. Hope I didn't make some kind of silly math mistake. I'm sure you caught me if I did. Does this converge? If so, to what? This, without the alternator, the limit as n approaches infinity of 2n over n plus 1 is 2. Now, if you stick the alternator on there, it's like it's bouncing back and forth between the odd terms approaching negative 2 and the even terms approaching 2. So the answer is no. That sequence does not converge. Explain your answer. I'm just going to say what I just said there. Odd terms are going to negative 2, and the even terms are going to positive 2. So you can't converge to 2 different things at the same time unless both of those things are 0, or the same number. So how about without the alternator? Yes, we just said that. And I'm going to use the compact and precise language of mathematics to say why. Explain your answer. Boom. There it is. How about the sum? So this does not pass the "you're telling me there's a chance" test. For it to have any chance whatsoever, the terms need to be going to 0. It doesn't even get over that low bar. Terms do not approach 0. Number 2, consider the series 2 over 1 plus 4 over 2 plus 8 over 6 plus 16 over 24, and so on. Write the series in sigma notation. I'm going to leave that blank because I might choose to start at 0 or 1, depending on how things line up here. Now, we have to figure out what is going on here. What numbers are these? These are powers of 2. This is 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, and these are numbers that you should recognize if you're going to be doing calculus with sequences and series, well, with series. These are the factorials. 1, 2, 6, 24, 120. This is 1, 2 times 1, 3 times 2 times 1, 4 times 3 times 2 times 1, and so on. So that's 1 factorial, 2 factorial. So what do we have here? It looks like I have 2 to the n over n factorial. Does this series converge or diverge? Justify your answer. Well, gee, I don't know. It looks like a ratio test problem because it's got a factorial in it. So if you're thinking, wait, how was I supposed to know to do the ratio test? Nobody said do the ratio test. Well, that's the way it goes sometimes. So it's the limit as n approaches infinity. Sometimes you just have to think about, what would I have to do to answer this question? 2 to the n plus 1 over n plus 1 factorial. Then I'm dividing by that, 2 to the n factorial. I'm going to try to simplify that. So on the top I have an extra 2, on the bottom I have an n plus 1, and as n approaches infinity that goes to 0. You might have suspected that. You have a factorial on the bottom. That is very powerful, driving it down to 0. So this converges because ratio test. That all of number 2, I think. Number 3. We can write this series in sigma notation. There's kind of a little bit of a red herring there in that this next one, this 1/2, that might throw you off, but of course 1/2 is the same as 5/10, so that just got reduced. That's all. Okay, so what's going on here? Well, looks like I just have a 5 on the top all the time. And on the bottom, I have numbers that are going up by 1, but it starts at 7. So if I wanted to start here at 1, then this would have to be n plus 6, right? All I'm doing is just matching that up to get the right first number. All right. Does this series converge or diverge? Well, thinking. What are the tests that we know? What does this look like? Hopefully you've taken some time to think about that. This is a limit comparison problem. By limit comparison, the series 5 over n plus 6 behaves like 1 over n which diverges because it's the harmonic series. You could say it's a p series with p equals 1. Harmonic series. another part. Part C. Find the smallest number n such that the partial sum S sub n is guaranteed by the alternating series error bound to be correct to 1 decimal place. Okay, so what does that mean? 1 decimal place means that we need to put a 0 at that decimal place and then a 5, right? We did some problems like this. And the alternating series error bound says that the next term, like the n plus 1 term, needs to be less than or equal to that for this to work. So, what is the n plus 1 term of this? The n plus 1 term is 5 over n plus 1 plus 6 is n plus 7, less than or equal to, that's the same as 1 over 20. So that means n plus 7 is going to have to be greater than or equal to 100. So if I want the smallest number n, it's going to be 93. What does that mean? It means that if you want to have a version of this series that's good to the first decimal place, you have to take 93 terms of it, which is an indication, like this is a harmonic series type of thing. These just, they converge very slowly. Very slowly. Oh, did I forget the... I forgot my sign alternator here. I would like the first term to be positive. So since I'm starting at 1, I'm going to have to do n plus 1 there. Sorry about that. That's good now. And notice that when I'm doing limit comparison, oh dang it. Does the series converge? So this would be true if it did not alternate, but it's not true because it does alternate. Does it converge? Yes, because terms alternate and the absolute value of the terms is going to 0. Sorry about that. Glad I caught it. All right, last one. Consider the series this. It looks like there's some factorials on the bottom of that. Write it in sigma notation. So I've got 3, 6, 9, it's like multiples of 3 on the top. Nice that whoever made this up, it was me, didn't reduce these. It would be way harder to see what was going on if these were reduced. All right, so let's see. On the top, I have multiples of 3. So that's when, as n goes 1, 2, 3, 4, that'll give me the multiples of 3. And on the bottom, I have factorial. Now, if I started at 1 here, which is going to work for the top, then on the bottom it looks like I actually have n plus 1 factorial, because I'm starting at 2, and then 6, and so on. This is 2 factorial, 3 factorial, and so on. So that's one way to do it. You could also start at 0 and make this 3n plus 3, or 3 times quantity n plus 1. That would work too. And where you need to alternate signs too. And I want the first term to be positive, so I need the plus 1 there. Okay. Does the series converge or diverge? If it's alternating, this is an easy case to make because the terms are going to 0. alternates, and the limit as n approaches infinity of terms are going to 0. That's all you need. But I should have asked you in this question, does it converge absolutely or conditionally? It converges because it's alternating, and but we have the because it's alternating. Would it converge if it wasn't alternating? Then we could say it converges absolutely. So to figure that, we would do the ratio test, because I see a factorial there, so I'm thinking ratio test. The factorial is on the bottom, so my gut tells me that the ratio test is going to give us a confirmation that it does converge, and therefore that this converges absolutely. But I'm going to do it anyway, because it's the right thing to do. N plus 1 term. When we do the ratio test, we throw out the sign alternator. We don't want that in here. Okay. Here, 3n plus 3 over 3n, and then on the bottom I have an n plus 2. So looks like I have n on the top, n squared on the bottom. The power on the bottom is higher, so that is going to go to 0. Learned that in chapter 2. So our series converges. We already knew that, but now we know that even if they were all positive, it would still converge. And last part here, I guess that was A and this is B, is use the alternating series error bound to show that, I'm going to try to show that S minus S4 less than 1 over 40. Okay, well, I know that the difference between, this is like the error between the real sum, which is who knows what, the error between the real sum and the partial sum of the first 4 terms. And I know that the alternating series error bound says that the difference between the real sum and some partial sum is going to be less than the absolute value of the next term. Okay, so if that's true, then what I need to show is, what is that 5th term? The 5th term of this would be 15 over 720. And I think I better reduce that so I can compare it to 1 over 40. It looks like I can divide, I think 15 actually goes into 720, doesn't it? Look at this, I can do some old school math here. 15 goes in there, 15 times 60 is 4. That's pretty close. And then 15 into 120 goes, let's see, 8 times. Now that's the same as 1 over 48, and 1 over 48 is less than 1 over 40. And this line is a math way of saying exactly what we need to say, right? There's no words that I need to do. I show that this is less than the next term, which reduced as this, which in turn is less than 1 over 40. And by the transitive property of inequality, less than in this case, we have accomplished our goal.